Okay, welcome to the Infosys Chandrasekharan Random Geometry Colloquium. We're very pleased to have today with us Jayadev Athreya from the University of Washington, who is going to tell us about variance estimates for geometric counting problems. I'd like to ask everyone except Jayadev to please mute yourselves for the duration of the talk. It will be a 1-hour talk, and then we'll have time for questions. This is the first in a series of 3 talks that Jayadev will do. Over to you, Jayadev.
Thank you, Anish, and thanks for this opportunity. I've been following the center. It's very cool to see this, and I'm very excited to speak to an audience of people with different kinds of expertise in random geometry. I'm going to speak on a very particular perspective on things, which is a kind of very continuous perspective. Often when you hear about random geometry, people think about, maybe you have some collection of discrete objects and you put them together, like an Erdős-Renyi random graph, or a surface built out of triangles with some kind of, maybe you pick some random permutation, or a surface built out of squares where you glue edges in some kind of random way. Those are all incredibly interesting objects. I may try and hint through the later talks about some potential connections between more discrete models and the continuous models I'm going to talk about. But what I'm going to really talk about, the thread that will link the 3 talks is sort of continuous families of geometric structures on fixed topological objects. So we're going to talk a lot about things that are called moduli or parameter spaces. And moduli or parameter spaces are, you fix some kind of topological structure or some topological object, and you vary, and this is my own idiosyncratic thing. This is not a mathematical definition. This is kind of an impressionistic thing. And you vary the geometric structure. And again, I'm going to give you lots and lots of examples. As I was warning Anish before the talk, especially this first talk will not really be one directed at experts in the area of homogeneous dynamics or the geometry of surfaces. This is intended for kind of a very broad audience, introducing you to the idea of these moduli spaces. And then we're going to define some interesting probability measures on these spaces. And these measures are going to be kind of natural probability measures. They'll be natural in some, there'll be some natural systems of coordinates on these moduli spaces or parameter spaces. And these probability measures will be, in some sense, a kind of Lebesgue measure with respect to these coordinates. So maybe I'll put, these are kind of natural probability measures. And then we're going to talk about sort of objects selected at random using these probability measures, selected at random using these measures. We're going to talk about the expected value of certain counting functions. Mainly associated to counting some kind of curves, associated to basically counting some kind of closed curves, which correspond to closed orbits for certain dynamical systems. Closed curves. And then the main theme of the talk is the main new results are going to come where we're going to try and understand, instead of expectation, we're going to try and understand variance and potentially and other higher moments. So expectation in a lot of these cases is going to be some really beautiful classical work. And then we're going to talk about the new work, which is going to be variance and higher moments. So this is the overall plan. All 3 talks will kind of follow this plan. I'll introduce you to a moduli space. I'll introduce you to a probability measure. I'll define a kind of counting function. I'll talk about expected value. And then I'll talk about the new work, which is the variance and the counting function. And so basically in the first talk, in talk 1, so today's talk, I'm going to talk about the space of flat tori first in 2 dimensions. That'll be the first thing we're going to talk about. Then we're going to talk about the space of flat tori in sort of higher dimensions, be bigger than 2. And what I'm going to talk about today, there's going to be some work of my PhD student, Sam Fairchild, which I'll mention. And then I'll mention some joint work of myself with Margulis, which is based on some really beautiful work, classical work of the mathematician C.A. Rogers. So that's going to be talk 1. Talk 2, or maybe since I was using Roman numerals, let me stick to that. Talk 2 is going to be, I'm going to talk about the space of what are called translation surfaces. And I'll define what these objects are. And then we're going to talk about what's called the Masur-Veach measure on these translation surfaces, or actually should be called really the Masur-Smiley-Veach measure. Maybe I'll put Smiley in there as well. Measure. And then we're going to talk about work of Veach. And then I'll talk about work of myself together with Cheung and Howie Masur on variance. And then in the third talk, we're going to talk about the space of hyperbolic surfaces. So we're going to, instead of changing from tori and going in higher dimensions or looking at sort of flat polygons, we're going to look at France and a graduate student at Stanford named Francisco Arana-Herrera on the variance of a certain counting function that Mirzakhani introduced. I will try and liberally sprinkle through references to survey papers and important papers in these things. Also, what I'll do is, even if I don't remember to do it during the talk, is I'll send Anish an email with some key references, and then he can send that out to the list talk so you can have some reading. Also, feel free at any point to ask a question during the chat if there's a definition or if there's a question on what I'm saying. Obviously, with the Zoom format, it's hard to gauge the reaction of people in the room. So please do let me know if there's something I'm saying that's very confusing. Okay, so that's the plan. And so let's start by talking about the space of flat tori. So what is a flat torus? Of course, we've all kind of seen probably various pictures of a flat torus. For instance, maybe you take a square here and you identify, maybe I'll think about the square as sort of sitting inside the complex plane. So maybe this is C here. So this is the point 1 and this is the point I. And maybe what I do is I kind of identify this side to this side and this side to this side, the left side to the right and the top to the bottom. That's basically the same thing as taking the plane and quotienting it out by the Gaussian integers, C mod Z adjoined I. And this quotient, of course, it has many different interpretations. C is an abelian group, so Z adjoined I is a normal subgroup. So this is a group. If you like that perspective, this is, it's an elliptic curve, right? If you like algebraic geometry or if you like group theory. But from my perspective, what's interesting is that Z adjoined I, when it acts on C by translations, it's acting via Euclidean isometries, right? So this action preserves the plane, it preserves the flat metric on the plane, and the orbits are discrete. So this quotient is a perfectly nice space. It's a really nice, it's a Hausdorff topological space. It has this Euclidean structure. If you like complex analysis, the action by these Euclidean translations is also holomorphic. So you have a Riemann surface structure.
Also president of the National Farmers Union, Minette Batters. Morning, Minette.
Good morning.
So C mod Z adjoined I is a Euclidean, it's a Riemann surface, it's a flat surface. So this is, so here this is, this is a flat torus, and this is a particularly special flat torus. Maybe we can call it sort of T2 sub Z adjoined I. But now you might say, well, Z adjoined I is not the only sort of group that acts discretely on the plane and gives you kind of a similar looking quotient. By the way, if I can draw a schematic picture of the quotient, here maybe I'll draw with some colors. Maybe this is the red curve, and that looks like this on here, and maybe this is a blue curve, and that looks like this on here. It's another curve. Of course, really a geometrically accurate picture. You can't really embed the flat torus inside of R3 in a smooth way. You can do it in a C1 way, but not in a smooth way. But the point is, there's nothing special about Z adjoined I. There's nothing special about 1 and I. For instance, I could have taken, thank you, T. So I could have taken, for instance, the lattice generated by any two linearly independent or linearly independent complex numbers. I could have taken, let's say, let me call them, let's say 1 and some tau, as long as tau is not in the real numbers, that generates a lattice. So I could take the lattice generated by that. Here I mean, so this is sort of A plus B tau, A and B integers. And I could look at the complex plane modulo this lattice. Let me give this lattice a name. Let me call it lambda sub tau, C mod lambda sub tau. And that would give me a different torus, T2 mod tau. So maybe here's a picture, maybe here's 1 again, maybe, or here's 1. And maybe here's tau is something like this. And then I would get some kind of different lattice. Now, this one I've actually drawn is a genuine lattice. In this case, I've picked tau to be, I think, 3/2 plus I. And I get this, one thing is that the area of this flat torus is different. So maybe that's kind of a cheap way of getting something different, right? I mean, obviously I can just scale things. If I really want to consider the geometries of different flat tori, maybe I should normalize and fix the area. I'm going to hold off on doing that for just a second because I'm actually going to, fix things in a slightly different way in just a minute. It'll be equivalent to fixing the area. But so here's a question, how can we build a space that encodes these different flat tori? So what I want is I want a point in the space to encode a flat tori. So that's question 1. And question 2 is how can we put a probability measure on it? Okay, so maybe a very natural thing to do is to say, let's think about the kinds of equivalents. Well, whenever we want to build a space of geometric objects, we really need a space of equivalence classes of geometric objects. So we need to talk about what we mean by when we say that two flat tori are equivalent. So if I have C modulo a lattice and C modulo another lattice, what do I mean when the two are equivalent? And maybe a good way of defining equivalence would be if they are kind of, geometrically the same, if there's kind of an isometry in between them. That would certainly preserve area. But maybe we also, since we already kind of saw that, one obvious thing we could do is we could just scale everything. Maybe we want to sort of quotient out by scaling and we want to quotient out by isometry. So maybe by kind of homotheties, just, scalings of the complex plane. In some sense, these are just holomorphic maps of the complex plane sending 0 to 0. We kind of want to quotient out by these guys, right? Just linear maps, C-links. So we want to say that, two flat tori equivalent if one can be sent to the other by a sort of C, I have C mod lambda is equivalent to C mod, let's call it rho lambda, if rho is any complex number, right? That's what we want to call our kind of equivalence, any non-zero complex number. Then what I'm going to do is I'm actually going to claim that I can select for you a natural set of representatives in an interesting way. using these things I defined before, these sort of lambda taus. Remember I said lambda tau was the set A plus B tau, A, B, and Z. So what I can do, what I'm going to do is I'm going to say, I'm going to take C mod, my favorite lattice. What I'm going to do is I'm going to take, let's say, Z0 in lambda is the shortest non-zero non-zero vector or non-zero number in lambda, zero element. That's well defined up to maybe some finite choices, right? Maybe there's multiple guys that are shortest, but let's say I'm picking just one of them. So it's one of the guys with shortest non-zero thing. I'm going to rotate and scale so that I make Z0 equals 1. So that is, I'm just going to scale, I'm going to replace lambda by Z0 inverse lambda. So now I have this guy has length 1, and it's the shortest. And then I'm going to rotate, so the second shortest is in the upper half plane. And I'm going to call that guy, call that tau. Okay. Sorry, I don't want to rotate. Sorry, I'm just going to say I'm going to take this. The second, I can always take. There is some second shortest vector in the upper half plane. If it was in the lower half plane, you can always multiply by -1, right? This lattice is closed under multiplication by plus or minus 1. So without loss of generality, I didn't mean rotate here. I meant without loss of generality, the second shortest guy is in the upper half plane, and call that tau. And then, so my new lattice, Z0 inverse lambda, is equal to this lambda tau, right? It's equal to this lattice generated by Z. And now, what I can do is, of course, there's still some ambiguity over this tau. I could replace tau by, let's say, tau plus 1, and I would get the same lattice, right? Lambda tau is the same lattice as lambda tau plus 1. It's the same lattice as lambda tau minus 1 also. So what I'm going to do is I'm going to move it around so that I'm going to choose my tau to just nail down some ambiguity, so that the real part of tau, sorry, not the real part. The real part of tau in absolute value is less than 1/2. So what I've done now, I'm kind of out of anything I can do. So what have we done? We have said, we have identified the space of flat tori is here's a picture. So it's the space of it's the space of lambda tau, where, so first of all, we know that the absolute value of tau is bigger than 1, because 1 is the shortest vector. So tau is longer than 1, and the absolute value of real part of tau is less than 1/2. So let me draw this in tau space. So maybe here is +1, and here is -1. So there, tau is outside of this, and then here is -1/2, and here is +1/2. And now, there is the space of these things. And now, of course, you could look at this, and you might harken back to what I said, and I said, oh, the measures we're going to define on these spaces are going to be kind of a Lebesgue measure. And now you should laugh at me, because you should say Lebesgue measure on this, that's infinite. How are you going to define a probability space? Of course, many folks in this audience know exactly how I'm going to define a probability space using this. The Lebesgue measure I'm going to define is not Lebesgue measure, not Euclidean Lebesgue measure. Instead, it's going to be a hyperbolic Lebesgue measure. So in fact, the probability measure sort of on this space of taus is going to be the following. It's going to be, the probability measure is going to be, I'll write it as sort of d mu is going to be, in this case, the normalization is 3 over pi. And let me write tau as kind of x plus iy dx dy over y squared. This 3 over pi comes from the fact that if you integrate dx dy over y squared over this region, so let me call this region, I'll just call it omega, is equal to pi over 3. So this is just a normalizing factor to make it a probability measure. So this is going to be my measure on the space of tori. Let me spend just 1 second talking about another way you can see this measure without using kind of complex things, using just linear algebra. But maybe before I do that, let me ask if there are any questions about this definition and the probability measure on the space of flat tori. So again, notice that this is kind of, one thing to notice is that this is kind of a very, it's a continuous measure. So for instance, by the way, just various probability things here, various points here, this is exactly the square torus. This is lambda sub what I was calling earlier just T2 sub I. So this is the square torus, lambda sub I. This guy is actually the hexagonal torus, or it corresponds to the rhombic lattice, as does this guy. These two lines are actually kind of identified to each other, these two vertical lines. As you go up this kind of red line, if you want to navigate in here, you're getting kind of longer and thinner tori, right? Well, I mean, they're getting longer. They're not actually getting thinner, but if you were to normalize them to have area 1, they would be getting longer and thinner. But so, you know, as you go higher and higher up, the tau is getting bigger and bigger. So, by the way, this space is just a couple of other remarks. The space is not compact, right? It's very much not compact. And the only way the non-compactness comes from kind of leaving out this cusp as you go up the top. I'm going to give this, actually, this omega is another way, another thing I'm going to call it by is M1 for the moduli space of genus 1 surfaces. So 1 here corresponds to genus of this rings. In talks number 2 and 3, we're going to hear a lot about MG, the moduli space of genus G surfaces. Okay, any questions? All right. Okay, so let me say another way of seeing this. So let's do some linear algebra instead. Another way of seeing this, and now I'm going to relax the equivalence a little bit. I'll want to say I actually care about, what if I wanted to understand kind of unit co-area lattices in R2? Let me, for right now, say up to rotation. Okay, and then I'll talk about, we're going to talk about what happens when we care about rotation as well. Well, to define a lattice in R2, I need 2 vectors. Let me call them, let me organize them like this. Let me call them, let's say V1 and V2. Let me give this matrix a name. Let me call it G. And if I want the lattice to have unit co-area, so maybe here is V1 and here is V2, what I need is I need this parallelogram to have area 1. So in other words, I just need the determinant of G to equal 1. That is, I need G to be in SL2R. And what is my lattice in that case? My lattice is just G applied to the integer lattice Z2. And so, of course, there's ambiguity in what G is. It's, in fact, what I really care about is I care about the coset of G, which is G up to SL2Z. So this is a coset in SL2R mod SL2Z. Because if I multiply G on the right by an element of SL2Z, Z2 doesn't change. SL2Z acts is the automorphism group of Z2. And so we have this SL2R mod SL2Z, and if I care up to rotation, what I actually care about is I care about kind of the double coset, so maybe I'll create a little bit more room, and I actually care about this double coset where I'm allowed to act by rotation, on the right, which is SO2. But those of you familiar with hyperbolic geometry, SL2R mod SL2 is, of course, the upper half plane modulo SL2Z, where SL2Z acts by fractional linear transformations on the upper half plane. And of course, the fundamental domain for SL2Z acting on the upper half plane. Here, let's see, how does SL2Z act? For instance, the matrix 1, 1, 0, 1 applied to an element tau just sends it to tau plus 1 over 0 times tau plus 1, which is just tau plus 1. And then the element 0, 1, negative 1, 0 applied to tau sends it to negative 1 over tau. Notice if I'm landing anywhere by moving, by applying this 0, 1, negative 1, 0, I can get myself from inside the unit circle to outside. And then by applying appropriate powers of this translation, I can get myself inside of this vertical strip. So these are exactly the same picture. The measures are exactly the same. But I do want to also say that one of the things we can do is we can also, if you care about things up to rotation, you can also look at the space SL2R mod SL2Z. I'm going to give this space the name X2. This is the space of 2D unimodular lattices. And here, what we and we can define sort of mu2 to be the probability measure on X2. And this is basically, if you think about this as the unit tangent bundle to the earlier thing, d mu2 is our earlier d mu, essentially times d theta, and then there's another divided by pi over there because the d thetas have a pi. So I see that there's a question in the chat. Let me take a look at that. Oh, Anisha's asking people to mute. Okay. So this is the Haar probability measure on the space of two-dimensional unimodular lattices. We're going to actually use this quite a bit. Okay, so half an hour in, I've introduced you. So now what do we have so far? We have a notion of random flat torus, and we have a notion of random unimodular lattice. And they're very clearly, very closely related. And so now what we're going to do is we're going to introduce the counting problem we care about. So here's the counting problem. So the counting problem we care about starts as follows. So given a flat torus, let's say C mod lambda tau, how many simple closed geodesics of length at most, let's say R, are there? We can call this is the random variable we care about. This is the counting problem we care about. So so we have to be a little bit careful with this question also, because, for instance, let's just look at my favorite torus, at least, this kind of square torus. So this is lambda sub I, right? So here we have this square with opposite sides identified. And there's really simple closed geodesics come in families. So we have this flat metric. We can talk about geodesics with respect to this flat metric. And simple closed geodesics come in families. So we're going to insert here passing through 0. Because otherwise, there's infinitely many. For every simple closed geodesic passing through 0, there's a simple closed geodesic passing through, there's a parallel family of these guys. So let me draw you a couple of examples of simple closed geodesics. And here simple means I want the geodesic to be, embedded. So I don't want it to intersect itself. So in particular, so here's some easy examples there. There's a simple closed geodesic. There's a loop that just comes back to itself. Of course, that's the same loop as that. Here's another one, this kind of blue. That's the same one as that. Well, let's draw some slightly more interesting ones. Here's a pink one that goes at 45 degrees. Maybe here's a green one. That's also a simple closed geodesic. If I were to draw it on this kind of one on this torus, it would wrap around kind of twice. I'm not going to try and draw the curved picture because I wouldn't draw it very well. This is what's called a 2-1 curve on the flat torus, for those who like things like that. Maybe I'll draw another one, which is maybe so this is 3 up and 2 across. So this would be a 2-3 curve. So there's that. That would go across. So I didn't draw it very well. It didn't look very straight, but it goes kind of, it wraps around 3 times that way. Oh no, there's another wrapping that I didn't draw very well here. Sorry, let's undo that last one. It goes kind of like this, and then, oh, sorry, I'm just not gonna draw the blue curve on the original torus. It goes, you know, its slope kind of 2/3, and it wraps around. Here's the key point. At least for this lambda sub I, what the simple closed curves correspond to is I claim that there's a 1-to-1 correspondence between this and the subset, and I'll define this in a second, z adjoined prim. So for C mod lambda I, it's z adjoined I prim intersect the ball of radius r. Simply means A plus BI, where A and B are in Z, and their GCD is 1. So for instance, something that doesn't give me a simple closed curve is maybe this, I'll use this kind of electric green. That isn't a simple closed curve because that just runs over the red curve twice. Okay. So here is the counting function that we're going to care about. So the counting function we're going to care about is, and actually I'm lying a slight little bit. What I want to do, given a flat torus, I'm going to call this C mod lambda tilde sub tau, where lambda tilde sub tau is the unit area representative of lambda tau, unit co-area representative of lambda sub tau. So if tau is sort of x plus iy, I'm gonna, you know, my lattice in these terms would be 1x or a y. So I replace it by y to the minus 1/2, x y to the minus 1/2, 0, y to the 1/2. That's the lattice I replace it by to make it unit area. This is just so the counting problems for all the surfaces are playing on the same footing, right? I don't want to be counting in kind of a different scale on different surfaces. So this is just the small change. And so then the question becomes, so I have this question. So maybe I'll call it sort of n of tau r, or n of gr if you prefer the linear algebra perspective. Maybe I'll n of gr, where this is sort of g sub tau is that, is the number of, in the following set, sort of, I'll write it like this. It's sort of a y to the minus 1/2 plus b times x y to the minus 1/2 plus I y to the 1/2. GCD of AB equals 1. So A and B here are in Z. Intersect B of 0R. That is, it is the number of primitive lattice points in the ball of radius R. You could also, you know, from the lattice perspective, you could also look, and this is not as natural geometrically, but you could also look from the lattice point of view at just the number of lattice points in ball of radius R. So from in the lattice point of view, these two problems are, you kind of look at GZ2 prim intersect B of 0R, or you could just look at all of GZ2 intersect B of 0R, and you could look at the counting associated with this. So, this is again kind of n of gr, or maybe n prim of n of gr, and this is n. Actually, I think I called the primitive one already this. Let me call n, let me give this a different name. Let me call this kind of m of gr, where I don't count with the primitivity assumption. So these are the random variables I'm going to consider. I'm going to pick g or tau, whatever you prefer, at random. Notice this question doesn't care about rotations, so I can happily go between g and, I don't care if I rotate the thing, right? Like the lengths of vectors don't change if I multiply by a complex number of modulus 1 or if I rotate by something in SO2. So it's okay, I'm a little bit sloppy going back and forth between the two. Okay, so now let me actually state that, so now we've talked about the random variable, we've talked about the counting, so we've talked about the space, we've talked about the random variable, now let me state the expectation result. So here is an absolutely beautiful result. It's attributed to Siegel, but it probably was known to Minkowski and Hlofka, but I think it's safe to call now. Everybody calls it Siegel. You should also probably, if you're talking about it to other people later on, Weil gives a far-reaching generalization. But here is the beautiful formula. If you integrate, let me actually write this as over sort of integral over SL2R mod SL2Z, just because it's going to be sort of the natural space where we do this, where I integrate sort of n of g r, and this is now d mu 2 of g. So if you remember, this is the kind of expected number of primitive lattice points in ball of radius r for a random lattice, random unimodular lattice, right? Because mu2, this is the Haar probability measure. By the way, this is just as a parenthetical, this is absolutely equal to this, integral over m1, as I called it before, kind of n of tau r d mu, which is the expected number of simple closed geodesics of length less than or equal to r on a unit area flat torus. And the beautiful theorem is that this is 6 over pi squared times pi r squared. So this is the expected number of lattice points in the ball of radius r. Let's say actually the slightly more general term, which is actually maybe makes it a little bit easier to prove more generally. If f from, we can say, is a bounded compactly supported function on C, you can think about it. So it's going to be my notation for bounded and compactly supported. Bounded, compact support. So nice enough functions. You can define f hat of g for g in SL2R. We define f hat of g to be the sum over so maybe z in z adjoined I prim, if you prefer, f of gz. Here, g acts on C by R linear transformations. I'm going to be a little bit sloppy going back between R2 and C. Let me know if that's confusing at any point. You can also think of this as f hat of tau if you prefer. And then the more general it states that integral of f hat, notice this really only depends on, this is Siegel, is equal to the integral equal to 6 over pi squared, the integral of f over c, just f of z dz over c. So you just integrate the function, you multiply by 6 over pi squared. You might ask, where does the 6 over pi squared comes from? Well, I mean, it really is kind of the same factor as this 3 over pi we talked about earlier. But let me give you a more kind of number theoretic heuristic for it. If you've never seen this before, it's kind of very pretty. For probabilists in the audience, you'll like this too, right? So 6 over pi squared is basically the probability that a randomly chosen pair of integers is relatively prime. What do I mean by a randomly chosen pair of integers? That equals the limit as kind of r goes to infinity, the number of AB and Z2, GCD of AB equals 1, A squared plus B squared is less than R squared, divided by the same thing without the GCD condition, right? So you sort of sample in this big ball, and how you see that is, well, okay, let's look at a prime P. What's an obstruction to two integers being relatively prime? The obstruction is, one obstruction would be if they were both divisible by the same prime. Well, what's the probability that they're both divisible by the same prime? 1 over p squared, right? The probability number is divisible by p. There's p residue classes mod p. So it's 1 over p that's divisible. The probability, if a and b are kind of independent, it's 1 over p squared. So the probability that they are both divisible by p is 1 minus 1 over p squared. And for those of you who have played around with Euler products, this is exactly 1 over zeta of 2. This is where zeta of 2 is summation 1 over n squared, n equals 1 to infinity. If you've never worked out this Euler product before, I urge you to do that. It's Euler. This is Euler, and it's absolutely spectacular to see this connection. So if you get bored in the rest of the talk, just work out that exercise. It's a lot of fun to do. Okay, so that's expectation. So now the question is, what about variance? So we're saying, the expected number of lattice points in the ball of radius r, or the expected number of simple closed geodesics, it has a finite expectation and we can compute it. So if you're a probabilist, the next thing you want to know, okay, what is this probability distribution? Is it sort of concentrated around the expectation? And the very first thing, if you want to care about concentration around expectation, is you should look at the variance. And then, of course, higher moments, the moment generating function, et cetera, et cetera. But let's start simple. Let's start with the variance. So let me actually first start by writing down something in higher dimensions, writing down a general formula for expectation, and then writing down a general formula for variance, and then I want to come back to the dimension 2 case. So now I want to all of a sudden jump up a dimension to d being bigger, d being bigger equal to 3. Look at the space SLDR on SLDZ is the space, so this is going to be the space x of d, the space of unimodular lattices in R to the D. Very, very similar construction, right? So G SLDZ is identified to the coset GZ to the D. And we're going to, again, we're going to define, for instance, if we start with the function which is bounded and compactly supported in R to the D, we're going to define f hat on x to the D to R by f hat of G is summation over, now we'll sum over vectors in ZD prim. So here, and I'll tell you in a second, f of GV, where ZD prim is V in Z to the D, where the GCD of all the components is equal to 1, right? So there's no, another way of thinking about this is these are what are called visible points. So there's nothing blocking you if you're sitting at the origin from seeing it. By the way, let me just take a pause for a second to reflect on what we're going to do, just to step back for the scheme of the 3 talks. I started a lot of the time today, we started with M1, and we started with kind of, there's going to be kind of a bundle over M1, the unit tangent bundle over to M1, or cotangent bundle, which was identified with X2, the space of unimodular lattices. The generalization we're going to look at today is kind of XD. We're going to look also in talk 2 at the unit tangent bundle to the space of genus G surfaces. This is going to be talk 2. And then in talk 3, we're actually going to look at just MG itself. So this is talk 1, talk 2, and talk 3. So this is increased dimension, and both of these are increased genus. That's why I spent so much time talking about this first example, because literally everything we're going to do is going to be a generalization of this first example. Okay, so now we have this f hat in this x to the d. Actually, Siegel's formula is much more general. Oh, and let me tell you the measure here. Mu d is the Haar probability measure on this space on XD. So SLDR has a Haar measure. Let me actually just take a second to define the Haar measure on SLDR. So SLDR has a Haar measure. You can actually construct it very nicely. So this is an SLDR invariant probability measure. You have a Lie group, it has an invariant probability measure. But here's what I'm going to draw is this is going to be the space of D by D real matrices. The joke, of course, always is that this is the picture of D equals square root of 2, because the space of D cross D matrices is D squared. And I'm drawing the schematic. This is just a schematic picture. And this is SLDR sitting inside. This is a locus. This is a level set of a function, right? Determinant is equal to 1. Now, D cross D matrices, that has a perfectly nice Lebesgue measure, which is SLDR invariant, right? SLDR preserves Lebesgue measure on, when it acts on D cross D matrices, it's acting on each column just by SLDR and just by multivariable calculus, right? That's preserving Lebesgue measure on each of these coordinates, each of these columns. So now what I'm going to do is I'm going to take some subset of SLDR, maybe this green subset. I'm going to define the Haar measure is actually just going to be a Lebesgue measure of this cone over it. So basically, if I have a subset, let's say A inside of SLDR, the Haar measure, mu of A, not normalized right now, is going to be the Lebesgue measure of the set of matrices TA, 0 less than or equal to T less than or equal to 1. This is Lebesgue inside of sort of D cross D matrices. That's clearly SLDR invariant, so it's Haar measure. It has to be Haar measure. And then, of course, there's actually a constant out front which tells you what the scaling is to make it a probability measure. That constant out front, if I want this to actually be, if I want it to be, let's say, this Lebesgue probability measure, it's actually 1 over zeta of D minus 1, all the way down to zeta of 2. Sorry, that's very small, but that's not going to be so relevant for our discussions right now. It's just something that's useful to know. Siegel actually computed it using what I'm going to tell you right now. There's a little bit of circular reasoning in what I'm telling you right now, because there's a back and forth between these integration formulas and these counting formulas. But let me state Siegel's formula for you in higher dimensions. Siegel stated, if you have this function and you integrate f hat of g d mu d over SLDR mod SL, over maybe I'll just call it x to the d, so I don't have to keep writing this. This is really an absolutely beautiful formula. It's 1 over zeta of d integral of f over r to the d. So with the same Lebesgue measure on here that makes the lattices unimodular. Okay. So now the question is, this is expectation. So for instance, the expected number of primitive lattice points in a set is the area of the set, so corollary. Expected number of primitive lattice points in a bounded set is 1 over zeta of d times Lebesgue measure of set, right? So that's an interpretation of Siegel's formula. Okay, so variance now is the question. Okay, so let me first state a result for d bigger than or equal to 3. And then, so this is a result of C.A. Rogers in the 50s. And I'm going to state it as actually kind of a second moment result. So what Rogers showed is that, so again, we still have our idea of f hat. Now we're going to look at f hat squared. So if you integrate f hat squared over x to the d, d mu, I'm now going to drop the kind of g's. That's equal to 1 over zeta of d squared, integral of f over r to the d quantity squared, plus a summation over pairs of relatively prime, let me say kq in Z2 prim, always 2 here, interestingly, integral over r to the d, again, of f of kx, f of qx, dx. So it's a very, very explicit formula. So it's saying that, you know, here, this is the kind of, this is, by the way, this is the expectation squared. This is expectation of f hat quantity squared. And so what this is saying is that the actual variance, which is the second moment minus the square of the expectation, is given by this. So sigma squared is the second term, right? So if we look at expectation of f hat squared minus expectation of f hat quantity squared, we get this summation down here. This summation integral r to the d f of kx f of qx dx. Okay, so I don't think actually, I think I might have to spill over into next time to talk about the proof of this result. But let me first start by telling you a heuristic of how we prove Siegel's result before we get to how we prove Rogers' result. Let me also maybe mention, just so we have this in this talk, and this is kind of important, and I'll spend a lot more time on it in the next talk. Rogers also claimed a similar formula for D equals 2. This, however, was wrong. And I'll explain next time why it was wrong. And it was recently corrected by my PhD student, Sam Fairchild. Fairchild gave a correction and a generalization to something called Hecke triangle groups. So I just wanted to mention her name because she corrected this mistake. It's kind of an easily understandable mistake in Rogers, but it's also easily noticeable. Once you notice it, it's easy. And Fairchild fixed this. Let me now mention a little bit how Siegel and Rogers thought about their results and how one would prove them in kind of modern terms. And then, or probably in the next time, I'll talk about an application on random lattices due to myself and Margulis, and then an application to polynomials, which is also due to us, which has beautiful generalizations by Anish, Dubey-Kelmer, Shucheng Yu. I'll try and talk a little bit about some of the work they did on random polynomials and random quadratic forms. Okay, but first let me tell you how Siegel's formula, how the proof works, or at least a heuristic. So let's go back to Siegel. Siegel says, you know, you have a bounded compactly supported function on r to the d. F hat of g is summation f of gv, v in z to the d prim. Then the claim is, that integral of f hat d mu d over xd is equal to 1 over zeta of d integral over f over r to the d. So f of x kind of dx. Suppose, let's black box the following. I'll come back to this. I'll just mention this black box. Suppose you believe that this is finite. Suppose, so that is, i.e. f in BC of r to the d implies f hat, sorry, is in L1 of xd. Suppose you believe that. Then f goes to the integral of f hat over xd d mu d. Okay, so what have I done? I've added f, the values of f over some vectors, and I've integrated, which is basically just adding again. So maybe I'll give this, let me call this a name. Let me call this t of f. This is a number, right? This is a number. And notice t of sort of, I have, you know, af1 plus bf2 will be a t of f1 plus b t of f2, i.e. t is a linear functional on BC of the d. So now think back to your first year analysis class. What are linear functionals? Linear functionals and so this, it implies that the sigma d, did I freeze?
Yes, you froze for a bit.
Okay, what's the last thing you heard?
First year linear functional.
Okay, so these things are linear functionals, but we have more than just linear functionals. We have SLDR invariance. Because our measure is SLDR invariant, that implies that this sigma d must be an SLDR invariant measure on r to the d. And there's only two interesting SLDR invariant measures in r to the d. There is delta measure at 0, and there's Lebesgue measure. And it's not too hard to see that delta measure at 0, oh, yeah, is not showing up because I've been summing over primitive vectors. 0 doesn't count as a primitive vector. Broadly speaking, 0 is not, that's the reason 0 is not going to show up. So sigma d has to be some scalar multiple of Lebesgue measure. Then what you do is you say, okay, if I were to take a really large ball, you might assume that this function, if you take f to be the indicator function of b of 0 r, and you think of r as very large, this function should be almost constant on my space. This is the number of lattice points in a very large ball. And by, you know, lattice point counting arguments, the f hat should be roughly 1 over zeta of d volume b of 0 r in r to the d. So that means sigma d should be equal to 1 over zeta of d dx, basically. d sigma d of x is just 1 over zeta of d dx. So this is a heuristic argument for Siegel's formula. This argument is one we're going to use over and over again. We're going to use this a lot in talk 2, and less so in talk 3. Talk 3, we're going to need new ideas coming from Mirzakhani. But this is going to be a crucial idea. We're going to define, and hopefully I'll have some time in talk 2 to also talk about a perspective that Anish and I kind of introduced formally, inspired by the work of a lot of people, of kind of the notion of an equivariant point process, which is basically inspired by the work of Veach and then the work of Markov. But in this language, it's been introduced by Anish and I. And we'll try and do that at the end of next week's talk to kind of unify the lattice story and the translation surface to it. But I've thrown a lot at you today. I'm about the end of my hour. So maybe I'll stop for now. I didn't cover everything I wanted to cover, but it's good. It gives me some things to talk about next, some more stuff to talk about next week. So thank you for your attention, and I'll stop for right now.
Thanks, Jayadev, for a fantastic talk. So let's thank the speaker. And if you have any questions.
Yes. Sorry. It wrote, it's for the measure that you define you define by this cone projection. It's a stupid question, but is it finite or is it infinite?
It's infinite. Very good question. I was a little bit sloppy about this. So this cone measure on SLDR is infinite.
Yes.
So har on SLDR is infinite.
Definitely. Right.
But there's a classical, and I should really, this is Siegel, and then, it's a special case of a deep theorem of Borel and Harishchandra. SLDR mod SLDZ is finite.
Okay.
SLDZ is a discrete subgroup of finite covolume. And so exactly as you say in the chat, as in this discussion between and Masur, that you can normalize it to be finite, and you normalize it. So in fact, the way I define the measure using this cone construction, it comes with the normalization, right? You have Lebesgue measure on D cross D matrices. And then to renormalize it to be probability, you exactly have to put this 1 over zeta of D factor out front. Well, sorry, not 1 over zeta of D, 1 over zeta of D, all the way down to 1 over zeta of 2. So in the normalization that I discussed, the volume is this product of zeta function. That's a result of Siegel. You can also do this, for instance, for symplectic groups. You can look at SP of 2GR mod SP of 2GZ. And then, just because this is beautiful, you only get the even values of the zeta function in your volume computation.
Yes. Thank you.
That's an excellent question. Thank you for clarifying that, because I think, that can get a little confusing.
Any other questions? So the talk is being recorded, and I'll put a link up on our webpage. So thanks again, Jayadev, for this lovely talk. So the next 2 talks will be at 6 p.m. India time, and next Monday and the Monday after. I'll send out reminders well before the talk. Okay, so let's thank Jayadev again, and see you all next month.